Hello, and welcome to this video tutorial on Wallacei Analytics. Wallacei Analytics is part of the Wallacei platform, which is comprised from Wallacei X and Wallacei Analytics. There is a complete video series on Wallacei X, which is a evolutionary engine and analytic engine, all within one single user interface on wallacei.com. And so it is highly recommended that you watch that lecture series, a video series, before watching this one. Wallacei Analytics essentially is a collection of components that allows you to reconstruct the graphs constructed within the Wallacei X components, but outside of the Wallacei X user interface. So any of the charts, such as the standard deviation charts, the parallel coordinate charts, the objective space, you can reconstruct these charts onto your Grasshopper canvas using any fitness values generated from any evolutionary simulation within, whether it was within Rhino or outside of Rhino, or essentially analytic tools for any type of data types. So as with the Wallacei X components, it is highly recommended that you look into the primer. The primer goes through each and every one of these components in detail, describing some of the equations behind them, describing the logic behind them, and how they function and how they might benefit you. So what I'll go through today is how to construct one of these components, mainly because all of them are very similar in terms of how you construct them. And I'll just quickly visualize these components in my Rhino viewport. So first thing I'm going to do is I'm going to use the fitness values I extracted from Wallacei X. So again, if you didn't know, if you didn't see the previous lectures, I recommend it. But what I did was that I essentially just took the fitness values that I generated from my Wallacei X evolutionary algorithm, and I internalized them, and I'm going to use these as a base for my analytics tabs. So under the Wallacei tab, there's the Wallacei Analytics, and these are the components that we will be looking at today. So the first component I'm going to be looking at is the standard deviation graph. And so I'm going to construct the standard deviation graph using the Wallacei 10 components, Wallacei X components. So all these graphs are very self-explanatory. So you need to define a plane, the scale of the graph, what are the fitness values and the generation size, what are the fitness criteria names, and so on and so forth. So I'll go through these now in detail. So first things first is the plane. So it can take any plane. The default is an XY plane, but you can use a point or a plane. So if I just draw a point on my canvas somewhere, and bring a point here, so that is going to change the position of the graph. I can control the scale of the graph. So let's say 0 to 2. The default scale is 1. So I can control how large or small the graph is. So I'll leave it at the default for now. Next, I need to insert the fitness values. Now, the tree structure for these components is a specific one. You can't just give any set of values in any tree structure. The tree structure is as follows. So the tree structure outputted by the Wallacei component is each solution is in its own branch, and each branch has 3 fitness values, because this problem was comprised from 3 fitness objectives, so I have 3 fitness values per solution. But what I need to insert in these Wallacei Analytics components is that each fitness objective, all the values for the entire population, has to be in different branches. Under the Wallacei utilities, there's a small component called Wallacei fitness values, and what this does is just literally changes or restructures my list so that it gives me the data type and the data structure that I need. So where in this case each solution was in a separate branch, in this case each objective is in a separate branch. So I have 2000 fitness values because I have 2000 solutions for fitness objective 1, 2, and 3, or 0, 1, and 2. So these are the fitness values, and I'm going to insert them there. Next, what I need to do is I need to define my generation size. So how many solutions do I have per generation? And in this specific case, I had 20 solutions in my generation. So I'm just going to put a slider value here with 20. And I need to also give it the fitness criteria names. What are the names of the fitness objectives? The default are fitness objective 1, 2, and 3. But for example, if I were to just create a list here, let's say maximize volume, minimize area, maximize height, for example, just any generic 3 names, it'll make the visualization of the graph much nicer. Lastly, which criteria do I want to analyze? So each graph will analyze a specific criteria. Because I have 3 criteria, so I'll go from 1 to 3. So this is criteria 1, maximize volume. Hide this guy. If I can switch to criteria 2, for example, or criteria 3. What I can also do is because criteria 2 or criteria 1 was to maximize, such as this case here, I can inverse this criteria. So 1 over x. Oops, apologies. So whether I want to, this is just a Boolean, actually. So do I want to inverse these values? So it inverses them to their actual values. And when running an evolutionary algorithm, to minimize, the algorithm essentially attempts to minimize the values towards 0. And that's how it optimizes a solution. But if you wanted to maximize a value, you have to inverse it 1 over the actual value. And that would drive it towards 0. So in this specific case, I had to do a 1 over before I ran the algorithm so that I can drive this value towards 0. But these values are just for the algorithm. The values that I'm actually interested in are these values here. And so these are the values that are actually indicative of what the volume is, for example, for each generation. So again, I won't describe what this graph is. This is a standard deviation graph, but you can find more about the standard deviation graph either in the primer or through watching the Wallacei X video tutorials. What this component can also do is it can cull boundary solutions. So each curve here is a generation, and sometimes you might have a generation that is so off or so extreme that that is kind of ruining the remaining curves. So you can't properly assess the full population because one curve is just completely ruining the domain of the chart. So what you can do is you can cull boundary solutions. So if I just put in a slider here from 0 to 10, for example, I can remove the solutions that are the maximum in my list. I first need to toggle whether I want to remove the largest values or the smallest values. So in this case, I'm removing the largest values. So you'll notice that curves are slowly disappearing. Maybe if I do for the smallest, it'll be clearer. So I expect that if I cull the first boundary solution, it's going to cull this very narrow one there. So if I make this 1, that curve disappears and everything remaps so that it can be properly or easily assessed. Now for this specific example, the domain is actually quite fine for all of the generations, but for some analyses that you might conduct on fitness values from your simulations, there might be 1, 2, 5, or 10 generations that are so far away from the norm that they might completely ruin the visual analysis of this graph. So you can continue to keep doing that until you are pleased. And finally, I can turn on and turn off the standard deviation steps. Again, this is all purely visual, doesn't really do anything to the calculation driving the chart. So this is just one example of how to construct excuse me, how to construct or how to use one of these analytic components, Wallacei analytic components. All of the remaining components follow the same logic. So I'll go through them briefly now, one by one. And but for more information, please go to the primer as it holds all information you need. So in this specific case, and this is the file that you will receive within the Wallacei download zip file, which is an example file, which is all of the charts connected properly. And so all you need to do is insert the values that you want, modify the generation size, modify the generation names, and select the criteria you want to analyze. So again, if I go back to the standard deviation chart, which is this one here, everything is connected properly. I can go back to the criteria to analyze and just go between them like that. So what I'll do next is I'll go through the second component, which is the standard deviation trend line. So this is also very similar to the Wallacei X component. The only major difference here is that it also shows you the actual trend line in the generation across the generations. So whether the standard deviation or the variation among the population is increasing or decreasing. And again, you can toggle whether to inverse the values so that you can actually better assess the true values of the fitness solutions. The next one we'll look into is the fitness values chart. And so again, very similar to the one in Wallacei X. Again, I can inverse the fitness criteria and you can go through the different objectives, 1, 2, or 3. Similar to the standard deviation chart, you can call boundary solutions and you can select a specific solution to highlight. So you can select which individual you want to highlight. So in green, it's individual in generation 2, individual 4. To better understand specific solutions in the population. And as with the standard deviation, there's the mean fitness value trend line. So this shows you the fitness average, the average fitness value per generation, and plot them on a line chart such as this one, where you can quickly highlight whether the mean average is, whether the mean fitness value is getting better or worse. So obviously we're trying to minimize the Wallacei X, or all these components indicate that the closer you are to 0, the fitter you are across a population. The next one is the objective space. So this is the only 3-dimensional one from this toolkit. And the objective space allows us to analyze the entire population. And what you can see in blue here is the specific solution that we selected. What is coupled with the objective space component is objective space analysis, or the Pareto front component. And in the Pareto front component, we can select a specific generation in the population and visualize the Pareto mesh for that generation. So for example, generation 19, that's the Pareto mesh for it and the solutions. And we can also toggle whether we want to project the Pareto on the planes, the X, Y, and Z planes. Next is the diamond chart. So again, we'll go back to top view. And very similar to the Wallacei X component, with the diamond chart, you can specify the scale. You can specify, so again, you can choose a solution according to 2 selection methods, either by the generation or the individual, which is this chart up here, or by the fitness objective and the rank. So for example, fitness objective 1, rank 94, is this solution here, generation 72, individual 2. Again, you can also inverse the fitness criteria through using a Boolean list. So I know that this is correct, so I'm going to keep that as 1. This is inversed and this is inverse. So what I want to do is I want to input 1, 0, and so it gives me the proper values for my fitness objectives. Last but not least, we have the parallel coordinate plot. And very similar to the parallel coordinate plots in the Wallacei X component again, we can inverse criteria. So again, I'll have 1, 1, 0 in this specific case. Oops, we'll have actually 1, 0, 0. But a feature that is available in this component that is not available in Wallacei X is that you can reorder the y-axes. So in this specific case, it's 1, 2, and 3. And that's the order of the fitness objectives: fitness objective 1, fitness objective 2, fitness objective 3. But if I were to make this, for example, 2, 1, 3, the chart changes so that you can better compare specific fitness objectives to one another. I can also compare, for example, only 1 and 3. And it's only going to compare 1 and 3 for me and omitting 2. So this also is a very, very powerful and robust tool to understand the relationships between the different fitness objectives and how that relationship translates to the solutions in the population. So I'll just revert this to 1, 2, 3. Coupled with the parallel coordinate plot is the parallel coordinate plot analysis. Again, very similar to the Wallacei X, we have 4 analytic methods, and they are highlighted here. They are highlighted in the primer. So please have a look at those. So for example, these are the most repeated fitness values. They're displayed here a little bit differently than in Wallacei X. So in this case, the wider the line is, the more fitness values have been repeated. And unlike Wallacei X, it shows the fitness values in this case, the repeated fitness values for all objectives rather than just one objective. Analysis method 2 allows you to extract the solutions associated with the most repeated fitness value. So for example, most repeated fitness value 0, these are the solutions for it. Most repeated fitness value 2, for example, these are the solutions for it. It gives you the number of repetitions, what that fitness value is, which objective it lies in, and what are the locations of those solutions. This is also given out as text file here for you to use or copy anywhere else. You can also elect whether to show or hide this data. Next is the solution with the relative difference, with the best relative difference. So in this case, this is the solution that has the most relative difference between solutions. And in this specific case, the fittest average rank. So those are the Wallacei analytic components. Be wary of using all of them at once, mainly because it's a lot of graphs, a lot of information, a lot of geometry, a lot of curves, and so on that is being displayed in the canvas at the same time. So it might be a little bit heavy, so just a word for the wise. But these are a very, very robust set of tools for users who are looking to better understand the results from their evolutionary simulation and better understand how they can extract specific solutions from the overall population. Now, if you are using Wallacei X, this data, all these charts, all these graphs are built in within that user interface, so it's actually much more robust, mainly because you can associate the solutions or the data that you're analyzing with the actual phenotypes that represent each solution. But these components are for those users who want to do further analysis, who want to extract any data, whether you want to extract the curves, the actual geometry, to continue your analysis or research onwards. So this is Wallacei Analytics. I hope you enjoy these tools and these components. It's a tool set that we found very useful for our research, and I hope it is for yours as well. If you haven't seen Wallacei X's video tutorials, I highly recommend it. If you have, then I hope you enjoy playing around with these tools. If you have any questions or queries or requests, please post on the Wallacei forum. The link is in the wallacei.com, and we'll do our very best to get back to you as quickly as possible. Thank you very much for your participation and for listening in to all these tutorials, and we hope you enjoy Wallacei. Goodbye.